All right, this is Bernoulli's equation. What it does is gives pressure in all of the forms it could take. So there are three main types. There's our initial pressure, which you might remember from when we talked about gauge pressure. That's usually just the atmosphere of the Earth. There is gauge pressure, which indicates, because it depends on height, that if you have a fluid in a container, and let's say your container changes heights from here to here, that the gauge pressure, rho GH, would change based on that height. And now you're thinking, but Mr. Melvin, you told me if we check the pressure anywhere, all be the same in a container. Well, yes, kind of. But now that fluid is moving. Remember, we're thinking about the fluid as moving. So the moving fluid changes height. This part of the pressure will change. But then there is this other kind of pressure that's kind of like kinetic energy. 1/2 rho v squared. So that pressure, some of its form might decrease, but some of it might increase. Pressure behaves like energy. It can take different forms. Your total amount will always be the same. So notice these totals are both the same, but it can take different forms. And let's talk a little bit specifically about what these forms are. So it can be kind of traditional atmospheric initial pressure. It can be gauge pressure, but something we should now think about, this gauge pressure is actually just potential energy per volume. So remember that rho is mass per volume, so this is mgh, just the m happens to be divided by volume. So it's potential energy per volume, and then this is kinetic energy per volume. Right there. And so your pressure can take all of these forms. It can take the form of initial pressure, just how much is that fluid being squeezed by whatever's around it. It can take the form of pressure because of height, and it can take the form of pressure because the fluid is moving. And whatever your total of all those kinds is right here in your container, that total will stay the same here. It will just be divided up differently between all of the possible forms. So, again, pressure can take many different forms, just like energy can take many different forms. And Bernoulli's equation just includes them all. So it is basically just Pascal's principle rewritten in all the types of pressure. So P1 can be all three of these. P2 can be all three of these. The total of all those three types is the same at any 2 points in the fluid. And if you're thinking, well, Mr. Melvin, I kind of feel lied to. You told me that this one, rho GH, was the same, or at least I thought that's what you were trying to tell me. Unless the fluid is moving. That's where it gets tricky. So if the fluid's moving, we've got to rewrite Pascal's principle as Bernoulli's equation. That's where the difference is. All right, let's look at the units in this equation just so you can kind of have that down. Okay, this slide just shows you what the units of everything are. I'm just going to encourage you to pause the video right here. There's not anything new as far as units. The only thing interesting is that these pressures will often be 1 atmosphere or 100,000 pascals. But pause to copy down the rest. I'm not going to talk through it. The rest is not new. What makes Bernoulli's equation nice is that often some parts of it will turn out to be 0. So let's look at this situation here. We have a fluid flowing through this container, so it's flowing through here, and the container changes cross-sectional areas. So we have one cross-sectional area here, a different one here, and a different one here. But this container doesn't change height. So the height of, think about it as the center of the container. So the height of that center of container doesn't change anywhere. So we are not going to worry about the changes due to changes in height. We're not going to worry about the rho gy part because the height doesn't change anywhere. So what Bernoulli's principle tells us, if we look closely at this, When the velocity is bigger, so if you look at this, pressure plus kinetic energy over volume, have to add to the pressure over here plus the kinetic energy per volume over here. So if the kinetic energy on one side increases, to keep these two sides the same, the pressure has to decrease. And so Bernoulli's principle tells us when the velocity is bigger, the pressure is lower. You need to take a second and pause the video if you have to and commit this statement to memory right effing now. When the velocity is faster, the pressure is lower. This is a really famous statement in physics. When you talk about Bernoulli to a physicist, this is what they think of. Oh, when velocity is fast, pressure is low. And so, the physicists who write the AP exam, because they are physicists, when the people giving them a list of topics say, we want some Bernoulli's principle questions, the physicists are just going to go, okay, well, velocity is big, pressure is small. So we'll write some questions about that. So if you commit this statement, just memorize it right now. You're going to be able to answer lots of questions on the AP exam with that factual statement. When velocity is fast, the pressure is lower. And let's look at a couple quick examples. What that would mean, so in this container, let's try to rank the velocities of all the places. We know that whenever the container has a cross-sectional area that's big, the flow slows down. So that was from continuity. Remember, A1 V1 equals A2 V2. So this part here has the biggest cross-sectional area, meaning the fluid would be the slowest through here. That means that the pressure would be the biggest, because when velocity is fast, pressure is low. So when velocity is slow, pressure is big. So right here, we would have a big pressure. Over on the right, we have the smallest cross-sectional area, meaning that this is where the fluid is the fastest. For pressure, fast velocity means low pressure, so this would be the lowest pressure. And then over here on the left, this cross-sectional area is somewhere between the other two, so it would be, I guess, a medium speed with a medium pressure. Medium speed or velocity, medium pressure. Okay? And so you do need to be ready to tie all of those ideas together. Big cross-sectional area, slow velocity, high pressure. Small cross-sectional area, big velocity, low pressure. I'm going to do this quickly because my videos are running long. Bernoulli's principle is how planes fly. So the shape of a plane's wing is made such that there is a greater distance for the air to travel up here, meaning that to travel that distance when the plane flies through the air, so the plane's speed doesn't change per part of the plane. The top of the wing is moving at the same speed as the bottom of the plane. But since the air has to cover a larger distance here, the air moves faster on the top. And you just found out from Bernoulli's equation that high velocity means low pressure. And so the pressure on top of a plane's wing is lower than the pressure on the bottom, meaning there is a greater force if the areas are the same. There's a greater force on the bottom of the plane because of that high pressure. And therefore, the air shoves the plane upward. Same thing with a frisbee, and if you want to pause and read this note on how a frisbee works, you can, but I'm going to move on.